All right, in this video, I'll be covering section 6.3, probably just the first half of it. We're going to talk about two different types of random variables, binomial and geometric, and talking about how to calculate means and standard deviations of each. So we have to first be able to identify what is a binomial random variable, what is a geometric random variable. So they go through a couple of examples here. Basically, if you're counting the number of successes in a fixed number of trials, we call this a binomial random variable. And if you're looking at a random variable that counts the number of repetitions until a success, we call that a geometric random variable. Both of these are discrete random variables, and that's going to be the focus of what we cover in this section. Okay, so toss a coin 5 times, count the number of heads. Spin a roulette wheel 8 times. Take a random sample of 100, count the number of females. Record how many times the ball lands on red. This is all a fixed number of trials. So it's just the same process 5 times, 8 times, 100 times. The trials are independent, so we call this a binomial setting. And the way that we check if something's binomial or not, we use this acronym BINS. BINS is binary. There's success and failure. Success could be rolling, what was this first example actually? Counting the number of heads. So success is heads, failure is tails, success is landing on red, failure is not landing on red. Each trial has to be independent. The number of trials has to be fixed, and the probability of success has to be the same on each trial. So you want to check, is this a binomial setting? BINS. If all of those are met, yes it is, and we can move forward and calculate probabilities based off of that. So the binomial distribution has 2 parameters. We've used parameters before with the normal distribution, so that shouldn't be a new term. The parameters for a binomial distribution are simply n, the number of trials, and p, the probability of success. So if we take a look at this example here, they want to know, are these binomial random variables? So we have blood type. We have 5 children. X is the number of children with type O blood. So success is having type O blood, failure not having blood. Independence, knowing one child's blood type doesn't tell you anything about the next, so I guess that you don't inherit any, what does it say? You don't inherit genes determining blood type from your parents, so that would make sense that it's independent. Number of trials is fixed, 5. Probability of success stays 0.25 on every trial, so that is a binomial setting. The second part, you're going to look at the number of aces you observe. So binary, you get an ace or you don't, success or failure. The problem is this isn't independent because you're not putting the cards back. So you're going to be more or less likely to pick an ace depending on what you pick on the first one. So this is just some examples of going through BINS again. I would pause the video now, work through this. So shuffling a deck of cards, putting the card back, shuffling again, getting an ace, not getting an ace, you're replacing, so you're fine. Number of trials is 10, probability of success stays constant. That would satisfy binary setting, so, or binomial setting, so that would be a binomial variable. Here this is not. You could have success being over 6 feet tall, failure being not over 6 feet tall, but you're selecting without replacement, so you're not going to have independence here. And the third one is not binomial because the probability of success is changing once one of the corner of the die chips off. Okay, moving on. That gives you an idea of what to expect and how to check if something is a binomial setting. So once we've identified something is a binomial setting, now we can start calculating probabilities. So because the events are independent, we're going to be able to multiply those. So in this case, we want to know what's the probability that none of the 5 children have type O blood. So it'd be not type O and not type O and not type O and not type O and not type O, 0.75 to the 5th. And you could have a lot of different probabilities where one person had type O. It could be the first child, the second child, the third, the fourth, or the fifth. So we start getting into some pretty complex calculations, and there's a formula that we're going to end up using to do this. And here it is right here. Okay, and this is on your formula sheet. This is going to be something that I'm going to be handing out this unit. We have the number of arrangements, which we'll talk about what that means, times the probability of success to the number of successes, times the complement, and how many failures you want. So the number of arrangements is this, n choose k. So on the calculator, it would be like 5 math probability NCR 1. 5 choose 1 is 5. So let me go back. So 5 choose 1 would be this scenario here. There's 5 children. We want 1 to have type O blood. So there's 5 different scenarios. Could be the first, second, third, fourth, or fifth child. So this is the way it's going to show up on your formula sheet. You don't need to know the factorial and how to do this by hand. Okay, so I just went through how to do this in the calculator. You're going to go to math. Well, type in the first number, math, go over to probability, choose the NCR. If you have an Inspire, there's a section in the back of the ebook that'll explain it, or you could YouTube it. So here's the official formula. This NK is the N choose K. Pretty intimidating. Let's see if we can't apply it and help make some sense of it. Let's see what we got here. All right. So in this scenario, find the probability exactly 3 children have type O blood. So I need to check bins. So they either have type O, they don't. The number of trials is fixed. Each person having type O is independent of the next, and the probability is constant. So don't want to forget that. So exactly 3. Well, I'm going to say X is the number of children with type O blood. And we have X is binomial, and the parameters are N is 5, P is 0.25. So what I want to do then is set up a formula. So I have 5 choose 3. I want 3 successes out of the 5 children. Probability of success is 0.25 to the third times 0.75 if I'm having 3 successes. Then I'm having 2 failures because I'm only looking at 5 children. And then I'm calculating this. Part B, should you be surprised if more than 3 children have type O blood? More than 3 would mean there's 4 or 5. So all I'm doing is setting up a formula for 4, 5 choose 4, plus 5 choose 5, and summing up those probabilities. The probability is 1.5%. That's less than our threshold of 5. So yeah, that would be surprising if 4 or 5 of their children had type O blood. There are shortcuts we can use in the calculator instead of having to use that formula. So let's go over those now. It's going to be under the same menu where you find normal distribution, normal CDF and inverse norm. It's going to be binomial PDF and CDF. Now this is extremely important. PDF is going to calculate the probability of an exact number of successes. So the probability of exactly 3 children having type O blood, you'll see binomial PDF 5 was the number of trials, N equals 5, P equals 0.25, K, or the number of successes, is 3. And that's going to give you that probability. Now, when we get into this idea of having multiple successes that we want to look at least at most, we're going to use binomial CDF. And that's going to compute the probability that it's number of successes from 0 all the way up until that number. But a lot of your calculators are going to offer you a shortcut. So let me see. So it's going to be under second bars. And if I hit the up arrow, binomial CDF. No. Some of your operating systems will offer you even more choices. Depends on what you have. This one does not. So if I type in my number of trials, 5, probability of success is 0.25. And the X value, that's the number of successes. So if I want them to have more than 3 children with type O blood, then that would be 4 or 5. So if I put a 3 here, this is going to sum up the probability that 0, 1, 2, or 3 of their kids have type O blood. And then if I do 1 minus this, that's going to leave me with the probability that 4 or 5 of their children have type O blood, which is what we're looking for. And that's what they're doing here. They're finding the probability that 0, 1, 2, or 3 of their children had type O blood, 1 minus that, similar to what we did when we did the at least 1 in Unit 5. So one thing to let you know, you can't just do calculator speak on your quizzes, tests, checks of understanding, AP exam. It's not going to get you full credit. At the very least, you're going to have to say like N equals 5, P equals 0.25, K or X, the number of successes, equals 3. Even better, write out your formula, but do the work in your calculator. Okay. There's a couple more examples here, exactly 2, so that would be a binomial PDF, where I'm just using the formula. I want 2 successes, I want 10 failures. You'll notice these are just complements, these probabilities. This is 12, choose 2. And then for the second part, they want to know that fewer than 10 win. Fewer than 10 would be 0 through 9. Because I'm starting at 0, I don't need to do 1 minus. I'm just going to use binomial CDF going up to 9. That's going to sum up everything from 0 to 9. Okay, so this check of understanding, why don't you pause the video right now and work through this? For part A, or number 1, it's just going to be going through bins. This is a binomial setting. Part B, it's the probability that exactly 3 of her guesses are correct. Finding that probability, it would be 10 choose 3 times 0.2 to the 3rd times 0.8 to the 7th. There's your 10 choose 3. This is the probability she guesses right. There's 5 answers, A through E, so 1 out of 5 chance, or 20%. We want 3 successes. So that means there's an 80% chance that she guesses wrong. If we're having 3 successes out of 10 trials, there's 7 failures. You could also do binomial PDF, N equals 10, P equals 0.2, X equals 3 to get that. And number 3, at least 6. So this is using 1 minus binomial CDF for N equals 10, P equals 0.2. And if I want 6 or more, then I'm going to get rid of everything 0 through 5. So when I did 1 minus the binomial CDF, my X number would be 5. And that's where that probability is coming from. All right, let's carry on to how do you calculate the mean and standard deviation of a binomial distribution. So the good news is there's formulas for you here. Basically, for the mean, it's just going to be, they're going to go through the proof here on how to get it from last unit. If you'd like to go through that, you can. I'm just going to go down to the summary. The mean is just going to be the number of trials times the probability of success. So if 10% of people are left-handed and we sample 100 people, 100 times 0.1, we'd expect 10 to be left-handed. And then the standard deviation is the square root of n times p times 1 minus p. These are the mean and standard deviation for a binomial random variable. If it's not binomial, forget these formulas. Okay, now some more proofs. Okay, this gets into explain why it's a binomial random variable. That's checking bins, find the mean and standard deviation using those formulas. So just looking at the interpretation, if this were repeated many, many times, the average number of students who guessed correctly. Okay, so this many, many times, it's going through the law of large numbers again. The correct number of identifications would typically differ from the mean by about, so that's the interpretation for standard deviation. And then they start to get into how likely, how unlikely is this? Well, then you can do binomial PDF or CDF to answer that question, or what we're going to learn eventually is you can use a different model. Okay. Multiple choice. Okay, so this one, n was 10. The probability of guessing right was 0.2. There were 10 questions, 10 times 0.2. So we'd expect on average kids are going to get 2 questions right. Standard deviation, the square root of 10 times 0.2 times 0.8. And what's the probability the number of correct guesses is more than 2 standard deviations above the mean? This starts getting into doing a little bit of calculations and then using the binomial CDF. I don't want to kind of get bogged down in that because we're going to talk about different ways you can do that. All right, I think that's it for binomial distributions. It is and it isn't. Things kind of transition here. I'm going to stop the video here. That's really the bulk of what we're going to do with binomial random variables and their distributions. In the next video, I'll talk more about binomials and transition to geometric.